All right,
Cool.
you're working now.
Thank you. So yeah, welcome everyone to our next talk in the EDT.Community online seminar series. Today we're very happy to have with us Bedir Tekinerdogan. Sorry, I'm going to be terrible at pronouncing every single name on these slides.
Yeah, it's a long name.
But I'll do my best. um, and yeah, so I'm just gonna, before we hand over to him, we've got a couple of things to mention. First off, we like to show some of the digital twin related publication targets that are coming up. One of those is ANSIM for next year, which is going to be being hosted in Washington from May 20th to the 23rd. And there's a submission deadline coming up at the start of the year in January the 14th. So yeah, please do note that down if you're interested in submitting to that. In terms of our seminar series, we have 2 talks booked so far. So yeah, we have Bedir today, and then in a couple of weeks' time, we have Judith Michelle on the 4th of December. So yeah, keep that in your calendars, and of course, we'll be sending out our usual mailing lists, invite and reminders. But yeah, as I say, today we have Bedir with us, and he's going to be talking about digital twin design patterns for system architectures. Bedir is a full professor and chair of the IT group at WUR. I'm not even going to try and pronounce the university name there. He has 25 years of experience in system and software engineering, experience in dozens of national and international research consultancy projects with various large-scale companies. And yeah, today he's here to talk about reusable digital twin design patterns for designing system architectures. And I'll hand over to you. Thank you, Bedir.
Thank you, Thomas, and thank you for having me. So let me just share the screen. Okay, you should see it now, right?
Yes, all good.
Good, yeah. So digital twin design patterns for system architecture. Good evening. If you happen to be in Europe. Let me just see. Right, so I am from Wageningen University, and then it says also like and research. That's the research institute part. So the idea is like to collaborate with the companies so they do more project-based research. We are in the social sciences department, so there are 21 chair groups there. My chair is called information technology, one of the 21. And we focus, this is our group, we're about 50 people. We focus on smart systems engineering. So it is a kind of a computer science group. Internally within Wageningen, we are quite a generic group because we collaborate with plant science, animal science, all the other science group. Or outside, we are kind of a niche group because we still focus on life sciences application domains. And in the last years, we have grown dramatically. So we started with 10 people in 2015, and now it's about 50 people, and so lots of research in different domains in life science, but also a broader. And one of it is, of course, the digital twins that we applied for different projects. I will talk about design patterns for digital twins. So that is thus like designing. So when we do this, apply digital twins, there's always a design activity. And when you do design activities, so sometimes you have to, you solve very often recurring problems. And for these recurring problems, you need sometimes solution templates, which we call design patterns. Many of you in engineering know these design patterns, but since the audience is a bit broader, I will also still explain what design patterns is, and then continue with the design patterns for digital twins. So this is the when we do engineering, as I said, typically we start with the requirement specification, we identify problems, and based on the problems we identify solution domain knowledge. Based on the domain, we try to define, identify, design alternatives, which we select based on some quality criteria. So that's the notion of engineering, very at the high abstraction level. But that's what we do, problem solving. We build things for using actually scientific knowledge. But in the end, it's all about problem solving. Well, what we see is like some observations. So as I said, you don't solve problems every day anew, but problems recur, right? That is, I mean, like we solved similar problems. And these problems seem to have same solution structure within a context. And what we also know, experienced persons, they know more. They can solve problems faster and better. That's what we know, right? So this counts for engineering, but also for other disciplines. Well, this combination is actually called pattern, right? So pattern, and I will elaborate on that. So novices, new beginners, they don't know many problems. They don't know many solutions. They cannot match problems with solutions. They have seen a few projects or contexts, and so typically solutions based on trial and error. Experts, as I said, they know many problems. They know many solutions. They know how to match these problems to these solutions. As we said, like experts know patterns. So we could say, abstracting from this, experience can actually be defined as the number of patterns that one know, right? So, and so in that sense, it's, patterns are very, very important, because if you don't know many patterns, so, or if you don't know these many problems and solutions and matching these, then you have, which implies that you have less experience. These are two brain scans from experts and novice. If I would ask, like, which one is from expert, it's the right one. So these are real. So that means, like, when an expert tries to solve a problem, right, that's not confused, like thinking all over all these brain cells are active. No, it's like that problem, solution, and then that direct match. So that shows also the effort that is required. So of course, patterns from the computer science we know. I started in the 90s, especially with the gang of Forza, the reusable elements of design. But before that, of course, like from they have borrowed the term from Christopher Alexander, or inspired from Christopher Alexander. What also Christopher Alexander said, like he passed away, I think, like last year or 2 years ago. What he said, like in his book, a very nice book that I read 10 years ago or 15 years ago. And when a person is faced with an act of design, what he or she does is looks at the pattern language in each mind. They are evolving. And an act of design, whether simple or complex, is just governed by patterns and combining these patterns. That is how we actually describe the design activity, when they're solving problems by applying these patterns, by applying combination of patterns. A pattern, as I have said now, it consists of a problem. You can see here a solution, and the matching of these two within some context. And problem is not any problem; it is a recurring, a generic problem. And solution is not just any solution; it's a solution pattern, solution template, and both actually defined in some context are described as patterns. So it's a kind of what Alexander says, a three-part rule: context, problem, solution. Patterns are discovered, are not invented, what we say. So you actually identify them based on when you have done several projects and you see some problems which repeat, which recur, and you see the similar solution structure, after which you say, like, hey, this is interesting. For this recurring problem, we have this kind of solution template. So in that sense, it's a kind of, it's a bit like a theory building. Right? So we have based on some problems, we have some scientific model, scientific pattern that we can reuse. Reuse is so essential here to solve new related problems faster and in better way. Well, so if that is so important, so useful, we should make. Why not make them reusable, right? So otherwise, it remains in the head of all these experts. So we said like that's also the notion of design patterns. Just describe them, give them a name, put them in kind of a pattern base or pattern catalog, so that other engineers, other people can reuse these patterns and design better, faster, and with higher quality. Right. So and that is essential. Of course, and this part. So what I should say, this idea is of course quite general. It's not just only to design, but it's also for any problem solving. You can identify this notion of design patterns. If you have some problem solving, and there's a book from Karl Popper, right? All life is problem solving. Everything is problem solving. Then we could say like, what are the repeating problems? What are the corresponding solution templates? So, and what are these patterns, right? So it is quite generic. Okay, then we said like patterns should be described, but how? Right? So Christopher Alexander used his three rule, the context, system of forces, and configuration. And based on that, what is quite interesting, this is also interesting, with pattern language. He defines actually 253 individual but related patterns, and because they are related, Alexander also calls them pattern language. Huh? So he starts at the very high abstraction level to the very concrete level, and this is basically from starting at the towns, buildings, and construction. Right. So in that sense, it becomes a pattern language. The other notion, what I will show today, is like a digital twin pattern catalog. So they are not necessarily related, but if you make it the one related set of patterns, they become a pattern language. Here's an example of architecture pattern, example of Christopher Alexander. And when this more for internal architecture design, light on two sides of every room. That's called that one of the 253 patterns. But when people have the choice, they just gravitate to those rooms which have light on two sides. And why, you should not ask, but that's psychology. So you could test it from yourself. And you leave rooms which are lit only from one side. That seems to be this the pattern. And so if that's the case, is it like when you design such a building, what the solution template says, locate each room so that it has outdoor space outside it on at least two sides. And that is like what this is the preferred one. So when you design the building in such a manner. This is just one example of a pattern. And patterns says, and Alexander also says, like, well, patterns increase the quality of the artifacts of the systems that we develop, but also makes the life also easier, right? So it is also what he talks about, quality without a name, right? So he also used the term centers, but that's also related to, in a sense, to aesthetics and quality. And actually, with this pattern, that's quite interesting. It showed like it is aesthetics, or the art and the nature of beauty is not that subjective. It is also objective, because he showed it with many artifacts. And for example, for buildings, for bridges, for Turkish carpets, he showed like that the number of patterns that are in such systems, they increase the sense of beauty of these systems. And in that sense, he says like, well, look, beauty is not in the eye of the beholder. And that's now the what we often hear, the kind of misperception in my opinion. But what Alexander said, no, quality, it's also like it's also objective. I would say read these books. It's quite interesting, and also other books. So if I come back to software engineering, and we can say, so how do we use these patterns? Well, we start with the problem, and then what we do is like, we don't directly design or develop the systems from scratch, but we identify, look up some design patterns, which are typically described in a pattern base or in books, in catalogs. Then we try to, based on the problem, we try to identify whether there is such a pattern that solves that corresponds to this problem. And typically, yeah, in the engineering, in software engineering, we call them intent, right? So what is the intent of the pattern? If this matches with my problem, I say, okay, it is like this. Probably I can reuse this, and then you look at the solution template, you apply the template, and in that way you have the best possible solution for your problem, because these patterns are supposed to be representing the expert knowledge, which have been derived from experience of many experts, and as such also explicitly described. So that's the assumption. Example, as you know, the layers pattern. When we build software, typically we have sometimes, very often, we have to cope with different abstraction levels, and then we mix of low and high level issues. And then that's the problem. If that's the case, structure your system in such a way that you have several layers, so-called layers, and apply a layered rule that is like each layer is allowed to use the next lower layer, but it's not allowed to skip a layer, and it's not allowed to call back other layers, a layer which are above it. That's a solution structure. Why is this nice? Well, if you apply this rule, you can, for example, change the implementation of the lower layers. Right? So it is good for portability. It's good for understandability. Of course, it's also like separation of concerns. Each layer has its own concern, each units. In that sense, we say like, beautiful design, right? So that's like, and this is a generic pattern. It can be applied to many systems which have this problem. Okay, and then we have also like patterns at different abstraction, design patterns. This is, as I said, from Gamma et al., starting from 94 and even 93, the PhD thesis. Here they have like 23 patterns focused not on architecture, but detailed design. Example here, name adapter pattern. Often we have to take this problem. We have to convert the interface of a class into another interface that clients expect. Like here, client is the target. Client expects operation request, but you have an adaptee specific request. How can we adapt this? And you don't have the option to change this, to adapt this, or redefine this. What do we do? What the pattern says, like adapter pattern, subclass this, with some name, and then have operation request, same request, and I have this predefined. I can have a reference field to adaptee, redefine the request, return adaptee to a specific request. Solved, right? And the client can now just still use this request operation and not need to call this. This, of course, is useful for maintenance and adaptability, etc., etc. Yet more, we can even look at the code patterns, or which are also called idioms, because it's about programming code. The programming pattern is, of course, specific to the programming language. Several patterns have been identified for different languages. Here is one interesting from Java, fast, or in general, so fast synchronized initialization. Often you have to deal with large objects. So, and then you want to reduce the space, or you don't want to unnecessarily occupy space, memory space. What the pattern says, like, well, don't create the object initially, just create first a static object, and later on when you need to, only when you use the object, then create the object. Says like, so here to check, If object is nil, create the object. So if it was already created, use the object, but this ensures that you only create the object when it's just necessary, not before. Very, very useful. That's the background on patterns and patterns in engineering. Patterns have been applied in different domains, and here we said patterns are discovered, not invented. I should say these patterns that I will show were also discovered in the project that we did. The term is of course not that old, digital twin. Of course, but we had also like Internet of Things before, and people used the similar concepts. But nevertheless, I will explain the patterns for digital twins that we have identified, discovered. What is a digital twin? Of course, just to summarize for this community, should be known, but still, so what is a digital twin? Of course, it's the notion of twin. It's a twin of something, of what? Of a physical object, which is often called just physical twin, right? So then you have digital twin and physical twin. They are twin of each other, but especially the digital twin is supposed to have a representation, a continuous representation, synchronized representation of the physical object. It is continuous, and you don't get rid of it. So, and we say like it has rich representation, so it just mimics the physical object. Why is this interesting? Well, it enables that we can, it provides us the opportunity to do things at the digital twin and not at the physical object, physical twin. Why is that needed? Sometimes you cannot do complicate things on the physical object. So you can do simulations, or you can do predictions or analytics, right? So you can do decision making, etc., etc. So for different purposes, and there comes it also like for which purposes, and we will see like what are the problems, and that has led to the idea of the digital twin patterns. What I will explain are discussed also in these two papers that we have written already now 3-4 years ago, starting in 2020. So we had first like we first wrote the paper, which is more ontological. What is the digital twin? What are the key typologies? And why we said like digital twin is based on control systems. So I will show in the next slides. And then soon after that, or in parallel with that, we wrote the paper, what I will discuss today on the possible digital twin patterns. The digital twin, what is also interesting, is not just at the end, but it can be used throughout the whole life cycle. Right, so we consider the systems engineering life cycle. So even it can start at the product level, implementation, and even at the retirement. That is also interesting. So your physical twin, physical object can be dead, but your digital twin can still continue to live. And that's also interesting. And also imagine this is applied also to a human being. You have a digital twin of yourself. And then after a while, of course, we are not here in the world anymore, but your digital twin is, and that's interesting. This is not a hype. So we should be aware of that. And I wrote an article about it on the notion of digital twins, a modeling perspective to focus on this issue, because there's something happening in the history now, which is just also complementary and just a logical next step, actually, if you look at from the modeling perspective. If you look at the history of humankind, and before we didn't use any design, right? So physical objects, right? So because these objects that we built were just simple. After a while, these systems that we built became more complex. So there was a need to provide some design, right? So drafting, a blueprint, and then these physical objects were built based on this blueprint. So we say blueprint because they should match each other. But it's shown here, there's a lack. Right? It's not just like you have to. They are totally independent, so they are not connected. And then with digital twin, that is interesting. we say like, well, we have the model. The model represents the physical object, but the connection remains. And the connection remains all the time, and you synchronize, and that is interesting. That is interesting. You see, we say like no, we don't have just a blueprint for just creating something. No, we just keep the model, digital twin model, which was called digital twin, to keep monitoring, keep controlling the physical object. That is really interesting. And then we say, well, this is just in time, it's just a next logical step. If you think about this, you say like, well, it's not that big idea, is it? Actually not. So why didn't we use this 10 years ago or 20 years ago? It was not possible because, right? So yeah, we have the connection, continuous connection. It was not possible because we didn't have the technology yet. And we should understand also the idea of digital transformation, which happened in the last decades, right? So after the invention of the computer, so we started with the digitization, mapping documents to 0 1s, right? Digital parts, and then we had like lots of digital solution, digitalization. Sometimes people uh, 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 not misuse, but they used them like in different ways. They say like digitization, and then you think like they mean like digitalization, but it's digitalization is the use of digital technologies, IoT, machine learning, AI, edge computing, etc. Digital transformation is the next step, which has led and which we see actually happening, the disruptive change on our society, on everything, on all the fields. And if you are interested, you can read the LinkedIn article that I wrote, just to clarify these issues. And why was this possible? Well, so our computers became more powerful, we became cheaper, which became smaller. And we have now more hard disk, more memory. And so following the Moore's law, and everything actually doubled and doubled and doubled. And then we saw the exponential. And I said, like, there are limits to the physical computer. And then we had like multi-core, parallel computing, and we have like quantum computing. The story just continues, and it's not ended yet. But how is this related to digital twin? Well, this is an enabler for digital twin. As I said, we have the digital twin, digital representation, rich representation of a physical twin, and there's a continuous connection that was not possible 20 years ago, right? So, but it is possible now, and we can do a smart, fast decision making. We can do the analytics, we can do the simulation, thanks to the increase, the radical exponential increase of the computing power. As I said, all the things that I discuss here so are described in these two papers. Feel free to check them. So I think both are open access. So if not, I will be happy to send them to you. What we say, like here in this paper, the observation digital twin, well, the conceptual model that we actually start with was like, we have a physical object, and it is like it follows the control system. This is a high level model, conceptual model of a control system. Then what is it? We have a physical object. We need to sense the state of that physical object, because I want to make a representation of system, and based on that, actually, I compare the state with some goal, with some objective, and then I will have some delta. So what is like? Well, I compare with my goal. For example, if I can check the temperature should be 20 degrees. I check like it's 18, so the delta is like 2 degrees. Then I need to find the right decision. In this example, I would say, hey, turn up the heater. So I say like, give that command to the actuator, which turns up the heater. And so control system. Control systems have been applied in many systems, right? So in houses, in cars, etc. So of course, in many self-driving cars or autonomous systems, it is like usually just a control system, and a very refined control systems with sensors, decider, decision-making, actuators, etc. How does it fit with digital twins? Well, digital twin solution is a control-based system, but we said like we have the sensors. Well, what we see like these actuators, what we said, like these sensors and actuators are located at the physical object part, and the decision making and selecting or identifying the deltas and selecting the commands which will be sent to the actuator are at the digital twin side. Here you see like digital object space. Huh? Here we say like one object, but you could have multiple digital twins and multiple physical objects. The relation could be many into many. Physical object space. You see here, you already see some concepts. So the physical object space consists of all the physical object, digital objects, the digital twin. You see, but what we did, like we said, like what is a digital twin? Well, it's a control system. Yeah, what are the elements of control system? Sensing, decision making, actuating. And then we said, like, how should we actually distribute this to physical twin and digital? Well, we said, like, well, let digital twin typically decision making and the analysis, and the physical object, the sensing and the actuating. That was the starting point. And then we use the term, this is not from us, please, and this is also a nice paper from Jones et al., which defined the terminology. And this is not, so what these terms are important to know. Physical object is, or physical twin, as I said, virtual object or digital twin, physical environment, all the environment which holds all these physical objects, virtual environment holds the digital twin object, the state of the value of the parameters, realization is the act of changing, metrology, measuring, and the twinning, we say like the twinning, so we said like it should be consistent, connection, twinning rate, physical to virtual connection, twinning, virtual to physical connection. You see, that's, we can have twinning on both sides. That's interesting. And then we have this in systems engineering. You say like we will apply this in systems engineering. Systems engineering builds a system. So digital twin based system is a system. So and it has a digital twin and a physical object. They are both synced. And then we said we focus on architecture. That's every digital twin system. Every system has an architecture. An architecture is designed using patterns. I said, okay, what are the system architecture digital twin patterns? And there we identify the digital twins. Right? So we have like, we call them digital twin pattern catalog. That is a catalog that you can look up and based on your problem, find some useful pattern, digital twin pattern that can be used to develop digital twin based systems. I will go quickly over them. And here are them. So so in the paper we show both the static model but also dynamic model to just in the like patterns in traditional have been described. We just follow the same structure. And so we have digital model, digital generator, digital shadow, matching, digital proxy, restoration, monitor, control, and autonomy. 9 patterns that we have identified. But we said like, well, it's not fixed. Yeah? So other patterns can be identified as well. But this was a very nice starting point. And we actually are now working on identifying patterns for other systems. Right? So preventive maintenance, for example, we have now a PhD on that. Try to identify digital twin patterns for preventive maintenance. So how did we document these patterns? So name, life cycle, context, problem, solution, structure, and dynamics. We'll just show. Well, if we look at the digital model pattern, that's the first pattern. In a sense, and this is not, strictly speaking, not really a digital twin, but it says like, well, but for completeness, we have a digital model. Based on that, a physical object needs to be created. Here's the static model, the class diagram. Digital twin is about, so I cannot see this one. Oh, let me just, now I see it. Develops physical object based on digital twin, and here's the interaction diagram. So client gets a blueprint, we get the blueprint, based on that you develop the physical object. This is the easiest one. The next level is like, right, so digital generator pattern. Digital generator pattern, we say like, I use the physical object. Now, physical object needs to be automatically developed based on digital object. This is in the spirit of model-driven development. I have a model, it's automatically generated. So it's like generate physical object says like get blueprint, and it generates automatically. It's not done manually. Next one, digital shadow pattern. Here say like I have a physical object. I want to create a digital twin of it. Huh? So that's like more, you get the state in some way, and then you get the state, and you define a digital object. You create it later on. Digital matching pattern. You say like, well, I want to, I have a physical object space. I want to find a physical object based on my digital twin, right? For example, in computer vision, machine vision, it's done like that. So you search blueprint, you ask the digital twin, it searches the blueprint in the physical environment, it provides the physical object, and then if there's a match, you provide the physical object. Proxy pattern, it's digital proxy pattern. Here we were inspired from the object-oriented proxy pattern. The structure is just similar. It says like a digital twin should act in case of a physical object. You see, say like digital twin is a rich representation of physical object. Then we said like, well, the digital twin can just serve as a proxy for the physical object, and that could be also for different purposes. Right? If you have a service, digital twin can do some pre-processing and then ask the service of the physical object. After that, can do post-processing, and then it can synchronize. Digital restoration pattern. So you have like digital twin is a rich representation of physical object. It can happen that the physical object collapses or loses its state. No worries. It says like, each time the digital object saves the state of the physical object. When something happens, some crash, it says like you can just say restore the state, and you get the state. Very useful, right? So a digital monitor pattern, we say like, well, here we went more to the ontological model of digital twins. We said like, well, I have a physical object connected with sensors, no actuators. I just monitor it. A physical object needs to be monitored by a human or external entity, like here. So you say like digital object gets a state all the time, and you have sensors connected at the physical object, and then you show it on the view, digital view, and you could have multiple digital views. One step ahead is like not just observing, but also controlling. You sense, you observe, but you also change. And so you change, you have an actuator here, which you did not have in the previous pattern, and you change the physical object based on your decision making. So, right, so you compare, so that's actually the full control pattern that I have shown before. And then also the digital autonomy pattern. If I go back, this is done still by human, by a client. Here say like, I don't need the client. I can just define my control values, and it thinks itself it will check itself. It will check the physical object, and then check the state, compare, identify the right action, change the state of the physical object, and even you can also add here some learning. 9 patterns, right? So it's like each pattern solves a particular problem. You don't need them for all systems, but it depends on your problem. And then we said like, well, how can we apply these patterns throughout the systems engineering? The systems engineering lifecycle, quite simply represented here. The concept stage, development stage, production stage, utilization, retirement. And we said like, well, which patterns can we apply in each stage? We said like, well, concept stage, typically digital model, digital shadow generator. And here the same. Here in the operational phase, of course, we can use matching, proxy, restoration, monitor, control, autonomy. Retirement state, it's like, well, retirement or the physical object got dead, right? Okay, the digital proxy still is alive, can still take actions on behalf of the retired or the dead physical object. We applied this, and also we were inspired from our case study, and it was typically from an Internet of Things project on farm and food, where we had several case studies, and we said like, well, let's apply and check how these patterns have been applied or could have been applied. So we did a kind of retrospective analysis, but also like looking also in the future, not really prospective, but what if it would have been applied. There were different sectors here, arable, dairy, and vegs. And then we look at each of these. This project is already over but we looked also at the documents. And then we said like, well, Here are the different case studies. And then we said, like, we looked at where each of these patterns had been applied with the name digital twin or not, and mostly without the name, because it was just before or just after the digital twin term had been introduced. But we saw, like, well, of course, I cannot see it here, but the digital autonomous pattern was not used yet, and the others, digital shadow, matching, digital proxy, were all used a lot. That is like in this IoT system, people made a digital twin representation. There was sometimes almost a real-time connection, and it doesn't need to be all very continuous connection. Also, if like this is sufficient time, that's fine. But the idea was similar. The related publications, you can look them up. So about this is selected one. We are still busy with the research and also have focused on different domains, including greenhouse, horticulture, now preventive maintenance, trying to actually elaborate on this topic and identify new patterns also within the domain of systems engineering, because then you see like that there are also lacking many issues. Conclusion. So digital twin-based system requires actually a holistic systems engineering approach. It's not just software engineering. When you design, it's good to look at the design patterns. So it's good to have pattern catalogs. If you didn't have a digital twin as a control system, there were no digital twin patterns. So we try to actually complement and contribute to the literature by identifying 9 digital twin patterns. In the future, we focus on other domains and implementation of all these patterns. Thank you for your attention. I hope it was all clear.
That's great. Thank you very much. Yeah, that was really interesting. So I'll open up the chat for questions. If anyone has a question, feel free to just unmute yourself. Then I'll call on people. I guess in the meantime, I did have